Neetu Kumar. Neetu Kumari is a highly respected researcher in the field of applied mathematics, currently serving as an associate professor in the School of Basic Sciences at the Indian Institute of Technology, Mandi. She earned her PhD in applied mathematics from the esteemed Indian Institute of Technology, Dhanbad, where her academic journey also saw her achieve notable distinctions with MPhil and MSc degrees. Throughout her prominent career, Dr. Neetu Kumari has continuously pushed the boundaries of knowledge in applied mathematics. Her research interests encompass cutting-edge topics such as deep learning algorithms for solving differential equations and mathematical modeling in ecology. These areas underscore her deep commitment to advancing both theoretical foundations and practical applications within her field. In addition to her background research, she is a dedicated mentor. She has supervised a diverse cohort of students, including 5 PhD candidates, 1 MTech student, and 1 postdoctorate researcher. Her guidance has not only led to impactful research outcomes, but also cherished the academic and professional growth of emerging scholars. Furthermore, she has published extensively with 48 papers in reputed journals, each contributing to the advancement of knowledge in her field. So her contributions extend beyond her research endeavors. She has successfully completed a significant project funded by SERB from 2019 to 2022, titled Modeling and Control of English Innovation in India, demonstrating her interdisciplinary approach to societal and inclusive dynamics. Currently, she leads a pioneering project funded by CSIR with a total grant of 20.17 lakhs, focusing on the development of deep learning algorithm to solve differential equations describing ecological phenomena. This project exemplifies her innovations approach to addressing critical environmental challenges through advanced computational methods. In addition to her academic pursuits, she actively contributes to the broader academic community. She is a valid member of the Indian Mathematical Society and has previously served as a mentor of SIAM, where her expertise and insights continues to influence and shape discussions at national and international levels. Today, we are privileged to have a such esteemed professor, Dr. Neetu Kumari, with us. So once again, I welcome you, ma'am. So over to you.
Thank you very much for such a nice introduction, Professor. And I would like to thank the conveners for giving me an opportunity to present my work here. So I would like to share my screen right now.
Yes, ma'am.
Please let me know if this is visible. My screen is visible?
Yes, ma'am, it's visible.
Okay. So without wasting time, I think I should start my presentation. Okay, so in today's talk, I will be talking about how these data-based algorithms can be very useful in understanding even those aspects of any infectious disease, which we cannot even touch upon using the traditional modeling approach. So it's more kind of a presentation where we will be doing a comparative study. We would be understanding the results that we can infer from the traditional modeling approach, that is compartmental models, and the data-based approach. For example, the help of some algorithms and using the real data for that. All right. So here in particular, we have considered COVID-19, and COVID-19 spread in India. And we have considered the data set of almost 3 years for modeling using the traditional approach. And for modeling using the data-driven approach, due to the complexity, we have considered the duration of 1.5 years. So what I will be talking about here is that, first of all, I'll talk about the motivation, what motivated us to pick up this particular technique to understand the COVID-19 spread, because usually you would say that you would see that in any infectious disease, the first approach that we do is the mathematicians, what the approach that we use is the compartmental modeling approach, right? So here we shifted a little bit and we thought that along with the traditional mathematical modeling approach, that is SIR, SEIF models, can we apply any database algorithm and what are the results that we can infer? So I would talk about why we are doing that. And then in the traditional modeling approach, we are talking about, we have actually discussed the results mainly. I'm not going into detail of the techniques, otherwise it would be very long. So I'll be talking about the results. So mainly the model fitting using the officially reported cases of COVID-19 for the case of India. Then we'll talk about the parameter estimations that we have carried out using the regression technique. We'll also be discussing in detail about the sensitivity analysis and the sensitive index of all the parameters that are being involved in the modeling. Coming to the data-driven approach, here we'll talk in brief about the algorithms that we have used, the DMD algorithm and compatible window-wise DMD algorithm. And we have applied both the algorithms to understand the data set available for COVID-19 in India. So we'll talk about that. Eventually, we'll go to the results that we have obtained using these algorithms and how what are the patterns that we are getting for the pandemic spread in India. We have performed the error analysis and we have also used these algorithms for the data reconstruction. So we'll be going into that also in brief. And whatever work I'm presenting today, it's already a published work. Anyone interested can go through this paper, which is in the footnote. All right. So coming to this COVID-19, it doesn't need any introduction. Everyone knows about COVID-19, and it has significantly impacted both the lives as well as the economy of several countries across the globe. So we are not talking much about what is COVID-19, how it spread, and where it went, all these things, because this is known to everyone today. All right. So we want to understand this COVID-19. We want to understand various factors that would have played any role in the spread of this COVID-19, or those factors which, when tweaked a little bit or controlled a little bit, could control the epidemic. So for that purpose, we decided to use compartmental models. So we have standard compartmental models like SIR and SEIR model. So we actually chose SIR model and its extension. So we had a 6 compartmental model that we formulated for understanding COVID-19. So what are the challenges that we face when we are dealing with compartmental modeling approach? So some of the challenges that we face is, first of all, the complexity that is involved in the compartmental modeling approach is little high. The equations that we solve are little cumbersome mathematically. However, these models can be used at a great length, and it can be proved to be very beneficial in terms of understanding the temporal dynamics, right? So over a period of time, how this disease is progressing over time. So that picture we can very clearly get from these SIR and SEIR models, or any compartmental model for that matter. Also, we can get a very clear picture of the different parameters or different factors that impacts the growth of the pandemic. So there also this our traditional approach is very helpful. So here, the mathematical model that we considered is presented. The schematic diagram of the model that we formulated for understanding the COVID-19 spread in India is presented here on the slide. So you can see it is a 6-compartment model, which consists of susceptible, exposed, quarantined, infected, isolated, and recovered compartments. All right. So here, again, this work, you can see the details in this paper, which is in the footnote given. So here, the individuals from the susceptible compartment move to the exposed compartment once exposed to the virus. And from this exposed compartment, Now, those individuals who did not show any sign and got recovered or by themselves, they moved to this recovered class at the recovery rate of sigma 4. Again, this exposed class, in this exposed class, those individuals who had some symptom, however, they were not clinically verified as infected, they moved to this quarantined class QT at the rate gamma naught. And again, those individuals who showed certain symptoms and they also were clinically verified using the COVID test as infected, they moved to this infected class. Now, from these two classes, those individuals who recovered, they moved to the recovered class at the rate of sigma 1 for Q and the rate of sigma 2 for I. However, those individuals who were not able to recover for a certain period of time, they were moved to the hospital and they were categorized as the isolated class. So Q and I moved at the rate of K1 and K2 respectively. So K1 and K2 is the rate of isolation. And now from the isolated class, so that those who are recovering, they are moving to the recovered class. So this is our 6-compartmental model that we formulated. So you can see actually this is a extension of our existing SIR model, not extension, rather it's a modification of SIR model. So we have S, I, and R, but we have included these extra 3 compartments. So once we have understood the schematic structure of the mathematical model, so the mathematical form that it takes, it is shown here, as we can see, with a positive initial condition. And all the parameters, its meaning is explained here. So A is your constant recruitment rate. Other parameters I have already explained in the previous slide. So once we have this model in our hand, now we want to understand the COVID-19 for India. So for that purpose, what we did, we considered a duration of almost 3 years, starting from 1st April 2020 to 28th February 2023. And the data that we considered was from the WHO site. So, right. So the data set considered is from WHO site. So what we saw is that there were the variations in the strategy for controlling the pandemic. It kept changing over this duration. Also, the variant of the virus, that also was changing. And the symptoms, that kept changing. So in order to actually successfully be able to mathematically model the COVID spread, we decided that we would divide the entire duration into 5 different phases. So the 5 different phases that we chose, and that was based on the duration at the time of the lockdown and the change in the symptoms and so on and so forth. So based on all these things, we divided the entire duration into 5 phases. So first phase was from 1st April 2020 to 14th Feb 2021. Second phase was, we chose also 15th Feb 2021 to 20th June 2021, and so on. Once we divide the entire data into 5 different phases, now we went ahead and we did the calibration of our model system on the officially reported cases. So here you can see in this figure 2, the red dots that are visible, these are the daily reported cases of COVID-19, which we have collected from the WHO site. So, here on the first row, we have the model calibrated for the real data set for different phases. So for the first phase, this is the model fitting that we did. Second phase, third phase, then this is phase 4 and phase 5. So once we did this model calibration, and also we did the parameter estimation. So we have in total 15 parameters involved here, on which the growth of the pandemic is depending. So we estimated all these 15 parameters separately for each of the phases, and then we did the model fitting. So once we obtained it for 5 different phases, we merged the result, and finally the model fitting looks something like this, as seen in this picture. This is 1st February 2020 to 28th of 1st April 2020 to 28th February 2023. So we can see this is an optimized model, and our model is performing pretty well in terms of its accuracy as compared to the officially reported cases of COVID-19 in India. So we are quite happy with this, and we move forward, and we want to understand the various parameters, what is the effect of these parameters associated on the dynamics of the pandemic. So here we have presented, so as I mentioned, the estimation of the parameter was done for each phase separately. So these are the parameters estimated for phase 1, this for phase 2, phase 3, phase 4, and phase 5. So again, as I said, we want to see the effect of these parameters, how these parameters are impacting the growth or the control of the pandemic. So for that purpose, we performed the sensitivity analysis. So we can see here that we have plotted the sensitivity index of all the parameters involved at for the entire duration of phase 1. So the first one is appearing here, phase 1, then phase 2, phase 3, phase 4, and phase 5. So this is actually giving us a pretty good idea about what are the parameters which is most sensitive for phase 1, the parameters which are more or less sensitive in phase 2, and so on. So what do we see here is that initially there were very less fluctuations in the sensitivity index of all the parameters. However, once we enter into phase 5, there is a very, the fluctuation is quite high, and mostly it is seen in K2. We can see the blue line K2, and this the orange line, that is this is your K2, and this orange line is beta 10. Okay, so there were huge fluctuations seen once we entered the phase 5. However, before that, the fluctuation was not that much, which shows that our disease, the COVID-19 spread, it became quite sensitive and sensitive in the final phase. So here, so the parameters that we saw, which were more sensitive, was sigma 2 and K2. So it was sigma 2. This is sigma 2, and the red one is sigma 2, and the blue one is the K2. All right. So sigma 2 is your recovery rate of infected individual. So what we see here is that the recovery rate of the infected individuals, the sigma 2, there is a huge, it's huge change in huge fluctuation in sigma 2. So as sigma 2 is decreasing, we can see it has reached up to near about minus 0.9 something, and K2, it is also near to 0.9, near about 0.9. So this means as these two parameters, if they are inversely negatively correlated, this is inversely proportional to the growth of the epidemic. So if these two are increased, the infection would decrease. So we could identify the parameters that, when controlled, can control the epidemic. So as I said, the phase 5 seems to represent a critical transition because of the huge fluctuation, or we can say high sensitivity of the parameter. However, from phase 1 to phase 3, most of the parameters exhibit minor fluctuations, not that huge fluctuations. Again, the parameter gamma 1, which is the rate at which exposed individuals transition to infected, it shows consistent and significant positive sensitivity across all the phases. So gamma 1 can be clearly, it signifies that decreasing the value of gamma 1 can significantly control the number of infected cases and eventually the pandemic. All right, in this figure, we have performed the PRCC analysis to find out the negative or positive correlation of the parameters involved. And we can see that K2 was identified as the most sensitive and negatively correlated parameter, as seen from this figure. So K2 is the isolation rate of infected individuals, which means if we have strictly implemented the isolation policies, then the epidemic could have been very well controlled. Now here, so the previous figure 4, here what we did was that we obtained the sensitivity indices for the entire phase on all the dates, and we tried to see how eventually these parameters sensitivity is growing over time. However, in this figure 6, what we are doing is that we are trying to see in each phase on the 30th day of each phase, which parameter is found to be most sensitive. So for that purpose, we performed the sensitivity analysis for the first phase, and we can see that for phase 1, the most sensitive parameter on the 30th day is found to be K2. That is, of course, the rate of isolation of the infected population. We move forward, and for phase 2, we are seeing that again, K2 is the most sensitive parameter, which can be seen from this figure. We move forward to phase 3, and we can see gamma 1 is the second most sensitive in this figure. It is visible. Similarly, phase 4 and phase 5. So we were able to identify what were the parameters which, when controlled or changed, can change the epidemic. So that gave us a pretty good idea about what is going on here in terms of the temporal dynamics. Okay. We also had a good idea about the temporal evolution of the pandemic. However, where we felt we lagged was that we were not able to capture how the disease is progressing in a spatial dimension. By that, what I mean is that, so we are able to capture over time that the disease is progressing, and it is decreasing and increasing, and there are various parameters when controlled can control the pandemic. But can we answer this question that from one state to another state, how the disease is progressing? For example, if the disease has reached to, say, Delhi on, say, June 25th, then how much time is going to take to reach to Himachal Pradesh? Or can we answer this question that if the peak has reached to Haryana on, say, June 30th, what time the peak is going to reach to, say, Delhi? Can we say anything about it? So we thought that this temporal approach won't be sufficient to answer these questions. And that is when we felt that we must move to the data-driven model. And we looked for some data-driven approach that can answer these questions. So coming to that, data-driven modeling can actually help us capture the spatiotemporal patterns of any disease. Also, in the traditional approach, the mathematical complexity is quite high. And when we apply this data-driven approach, we can expect little reduced mathematical complexity here. Another thing, if you compare this data-driven approach with the traditional modeling approach, so during the formulation of the mathematical model, we have to make certain assumptions, and we all know that the assumptions can affect the final result. So that problem is not there in the data-driven modeling. We also have see the accuracy of pandemic prediction highly depends upon the accuracy of the parameter estimated, and we estimate a parameter in the case of traditional modeling technique. So what happens in the data-driven modeling approach is that here in this case we have used dynamic mode decomposition to understand the dynamics of the epidemic. So using DMD, we are able to capture the spatiotemporal patterns, which is very, very important in order to, so which becomes utterly important in the implementation of preventive measures. As I said, the mathematical complexity involved is relatively less. Now about this DMD, which is a spatial dimensionality reduction algorithm. About this algorithm, it has been already very frequently used in the CFD research area. However, it was not being very frequently used in the understanding of any infectious diseases until Procter and Eckhoff very recently showed in one of his papers that DMD can be very helpful for understanding any infectious diseases. And when we conducted this study, on that date, there were no studies which were used to understand this COVID-19 in India using DMD. So that motivated us, and we thought, let us use it. So what did we do? So I'll just tell in brief about this algorithm, and then we'll move to the modification of this algorithm, that is compatible window-wise dynamic mode decomposition, which was really helpful in capturing the spatiotemporal pattern of COVID-19 in India. So I'll talk about it after a little bit, talking about the algorithm. Then I'll move to the result. I'm not going into the details. The details can be found in the paper which I cited at the beginning. So in order to apply this dynamic mode decomposition, what we do is that we construct a data matrix. We write present the entire data in the form of a matrix such that the rows of the matrix would be representing the spatial locations, and the column of the matrix would be representing the temporal locations. So mathematically, the matrix can be given as shown here, X showing here X0, X1, X2 up to Xm minus 1, Xm, where Xk belongs to Rn and K belongs to 0 to n. So these are across n matrix. Once we have done that, once we have this matrix in our hand, what we do is that this matrix X can be rewritten as two data matrices with a small shift, one time shift, one temporal shift. So X is your X0 to Xm minus 1 and X dash is X1 to Xm. So we have these two data matrices obtained from the original data matrix X. Now, the data set that we considered, it consisted of the data of district and the cases that were reported in the districts. So we had 640 Indian districts. In those 640 Indian districts, the data which we considered for the duration, it was from April 26, 2020 to 31st October 2021. So these are our temporal points, and this would be our spatial point. So as I said, the columns of this data, it would comprise of dates, and the rows would comprise of districts for this data set. So this is our data set looks something like this. So we can see here we have used two data sets. So the first data set is data set A. So we can see each of the column is district 1 to district 640. And sorry, each of the rows is from district 1 to district 640. And the columns is the dates from 1 to 554. So we have 640 cross 554 size matrix data set. Now, if you can recall, I said the question that we want to address, for which we move to this data-driven algorithm, DMD, is that we want to visualize how the disease is progressing from one state to another state or one district to another district over a period of time. So in order to visualize that, here we felt that the challenge, if we want to visualize it for 640 districts, it would be little challenging to make the analysis. So we decided to convert this dataset A into another dataset called dataset B, where we merged these districts into states and the dates into weeks. So now the new dataset that we formed, it consists of 36 states and 79 weeks. So now it is 36 cross 79 matrix. So now our data set is from 640 cross 554 to 36 cross 79. And we felt that now it will be much easier to visualize it, the spread of the disease. All right. So now this is the data that we pulled in, and for each of these states. So these are the cases, confirmed cases, as reported by WHO for India. So we'll be using this data set. Now, for application of the DMD algorithm, I would like to talk just in brief about this algorithm so that when I am talking about the result, it will make some sense. So as I said, DMD is a spatial dimensional reduction algorithm. Okay, and it analyzes the relationship between the future measurements and the previous measurements, previous data measurements. So using the future data measurements xk plus 1 and the previous data measurement xk, we try to find out this linear operator A using the DMD algorithm. So we first obtain this for all pairs of data, and then we merge it or we club it to obtain x dash equals to a x dash approximately equal to ax, or a is equals to x dash pseudo inverse of x. So once we have obtained this relationship, then it is easy to, once we have obtained this a, the linear operator, now the things are much easier. So the algorithm goes like this, something like this. The first step is to compute the singular value decomposition of this matrix X. The matrix X, if you can recall, it is the data matrix X, which we arranged for our data, which has the rows as the spatial points and the column as the temporal points. Once we have done that, we obtain A. So for obtaining A, first of all, we have to obtain the pseudo inverse X using this formula. Once we have obtained the pseudo inverse of X, then we obtain the reduced matrix A, a reduced matrix of A, that's A tilde. As I said, it's a dimensional reduction algorithm. So we get this reduced matrix A using this particular formula. Once we have obtained this reduced matrix, now we obtain its corresponding eigenvector using the spectral decomposition. So this is your A tilde W is equals to W capital lambda. Lambda is nothing but it's the diagonal matrix obtained from the eigenvectors. So once we have this eigenvector W, we use this eigenvector W in step 4, and we obtain the DMD mode matrix 5. Okay. So once we have obtained the DMD modes, our job is done. Now these DMD modes, once calculated, there are a few things, I would say a few measures that we obtain for this particular DMD mode, and we'll analyze our result. So those few measures that we are going to calculate includes the frequency. So the frequency of each of the DMD mode is given by this particular formula, as you can see from equation 3. There's the imaginary part of lambda logarithm ln lambda k upon delta t upon 2 pi. So this gives the frequency of each mode. And also these DMD modes can be used to reconstruct a dynamical system. That is the best part. It's not just doing the dimensional reduction, but it is also successfully giving us a dynamical system, reconstructed dynamical system, as given in equation 4. So once we have obtained this reconstructed dynamical system, here B is the initial amplitude given in equation 5. All right. Now, I must talk about so once we apply this DMD algorithm, I must talk about the compatibility conditions for application of this DMD algorithm. Your data set has to be compatible. So the compatibility condition for application of DMD algorithm is presented in definition 3. So it is the balance between the temporal and the spatial resolutions. That is the data set X with temporal resolution n plus 1 and spatial resolution n have the relationship m less than equal to n. Okay, so when this happens, then we can apply the DMD algorithm on the given data set. So if you can recall, the data set A is very much compatible to the application of DMD, because there we are satisfying the condition of n greater than equal to m, because the size of the matrix was 640 plus 554. However, for data set B, the size of the matrix is 36 cross 79. So we realized that we are not able to apply this dynamic mode decomposition there. So then we went for a modified version of this dynamic mode decomposition, that is compatible window-wise dynamic mode decomposition. Okay, so what do we do here? So it isn't, so I'll talk about this algorithm as well in brief here. The details can be seen in the paper that I cited earlier or in this particular paper. So what we do here is that it is an extension of DMD that takes into account the spatial structure of the data. It's based upon a key idea that the compatibility condition is satisfied, which is n must be greater than or equal to m. All right. So now, what do we do is that the given data set, we divide it into multiple data sets such that each of the data set must satisfy the compatibility condition. So once we have obtained the multiple data sets, which is eventually satisfying the compatibility condition for application of DMD, for each of the data set, we apply the DMD algorithm. So this is your compatible window-wise dynamic mode decomposition. So algorithm says, similarly, our algorithm is exactly same. We first generate the compatible data sets, looking into the size of the matrix, and then we apply the algorithm 1 to each data set. Okay, now the choice of the DMD mode is very important for the magnitude and phase analysis because we obtain several DMD modes. All right. So if we don't choose our DMD mode wisely, then it may not reflect the true dynamics. So choosing the selection of the DMD mode depends upon the power of the DMD mode. All right. So the power of the DMD mode is calculated by this particular formula as shown here. So once we calculate the power of each of the DMD mode, then we select that particular DMD mode which has the highest power. So higher the power, more significant is that particular DMD. All right. So after computing the modes with highest power, once it is done, that is choosing the most dominant mode, we further categorize the modes as decaying, oscillatory, or growing based on the position of the DMD mode. So what does it tell us? So once we can identify that your DMD mode is decaying phase, or oscillatory phase, or growing phase, it actually reflects the pattern of the disease. So whether the disease is, the pandemic is in the decaying phase, or oscillatory phase, or growing phase, can be told by the nature of the dynamic mode. Whether the dynamic mode is in decaying, if dynamic mode is decaying, this means the epidemic is in decaying phase. If the dynamic mode is oscillatory, then the epidemic is in the oscillatory phase, and so on. All right. Now, if the eigenvalues of the corresponding DMD mode lies inside the unit circle, it is classified as decaying. If it is on the unit circle, it is oscillatory. So this is the technical thing. Of course, the idea is that we must identify what is the nature of the mode that we have selected. Then we further perform the magnitude analysis, phase analysis, and error analysis. This is important. So by performing the magnitude analysis, we can get pretty good idea where, in which spatial location the disease is, the pandemic is more severe, and in which location it is not. That is told by the magnitude. So once we have identified the DMD mode, then we obtain the phase difference between the two variables, which is calculated by this particular formula presented here. Now, this phase difference actually does the trick. What it does, it tells the phase difference between two spatial locations would tell you what is the time lag, what would be the time lag of the epidemic to reach from one spatial location to the other spatial location. So here, this solves much of our problem and could help us answer questions like, if the peak is reaching to a certain state on nth date, then can we say when the peak is going to reach to another state on what date? So that would be answered by this phase analysis. So as I said, phase difference, we infer phase difference to be the time lag between the region-specific peaks of COVID-19 outbreak. And the error analysis for our technique is done using this particular formula as shown here. So now let us, once we have understood, we have understood a little bit about the algorithm, we'll come to the results that we obtained for COVID-19 in India. So since, as I said, the data set A was quite compatible and we applied DMD there. However, for data set B, it was not compatible for application of DMD. So we divided the entire data set B into 3 windows, and each of the window consisted of 26 weeks. And once we have done that, we applied compatible window-wise DMD algorithm. Okay, and we performed the magnitude and the phase analysis, and certain things were kept into consideration. So here we see the first result of the first window. So we obtained all the DMD modes, and so here this left panel shows the discrete eigenspectrum plotted against a unit circle, and this particular column, it shows the power versus frequency plot. As I said, that in order to understand that among all these DMD modes, we need to choose one DMD mode, one or two DMD mode to understand the epidemic. So in order to choose that, we need to calculate the power. So the DMD mode 1 and DMD mode 2 were found to be the modes with the highest power. So for this DMD mode 1 and DMD mode 2, we performed the phase analysis and the magnitude analysis as shown in figure 8b and figure 8c. So what we saw here was that we were able to capture the idea of which state has the highest incidence of the highest number of cases at that moment of time, that is in this window of April 2020 to October 2020. All right. So we can see the magnitude was highest for mode 1, the magnitude was highest for Maharashtra. Similarly, for in the mode 2 as well, the magnitude was found to be highest for the state of Maharashtra. We compared it with our data set. So we can see figure 8D are the officially reported cases for all the states. So here, weekly incidence of COVID-19 cases from April 2020 to October 2020. So here we can see that the highest number of COVID-19 cases were reported in the state of Maharashtra for that duration. So we were able to capture this. Now, coming back to the question that, can we say something about the peak reaching from one state to another state? So for that, we performed a phase analysis and we obtained the phase difference between the two states. And the results are shown here. So from the phase analysis, we observed that the phases of Punjab, Haryana, and Rajasthan were quite similar in both the modes. Now, the time lag between peaks of Andhra Pradesh to Maharashtra was found to be near about 3 to 4 weeks. And if we go back and see, then in Andhra Pradesh, the peak was seen in the 19th week, and Maharashtra, it was 21 weeks. So it is in our calculation of the phase difference was 3 to 4 weeks, and it is following the same range. Similarly, the phase difference between the peaks of Andhra Pradesh and Delhi, Karnataka, and Madhya Pradesh, it was between 3 to 4 weeks. So, and which matched with the officially reported cases. Again, we were successfully able to find out the time lag between the peaks of Tamil Nadu to Maharashtra, Karnataka, Delhi, and Madhya Pradesh was between 4 to 5 weeks, which matched with the real data. So once we have done that, we move to the second window, that is November 2020 to April 2021. Here again, we had this shows a discrete eigenspectrum plot from where we chose DMD mode 1 and 2 based on their power, which we can see here. Highest power mode was 1 and then 2. So we chose these two modes and we plotted its phase analysis and the magnitude analysis. And from here, we saw again this Maharashtra was one of the state, and here we can see Kerala was on the state which had highest incidence, and similarly here as well. And we checked with this, and we could see that the results that we are obtaining, it is matching with the uh, COVID-19 reported cases from WHO. Then here also we are able to, similarly, we are able to calculate the phase difference between the two states. And for example, here between the maximum phase difference between Maharashtra and Andhra Pradesh was compared to be 3.39 weeks, near about between 3 to 4 weeks, which was matching with the peaks of the COVID cases in these two states, and similarly for other states as well. Again, we repeated the whole thing for the third window as well. We identified the most prominent DMD modes and their power. Based on their power, we plotted the phase and the magnitude analysis, and the results were satisfactory. Now, these important questions: how the spatiotemporal spread is there of the COVID-19 in India, when the peaks is reaching from one state to another state, how much time it is taking, and so on. So now we use this algorithm for the data reconstruction. So you can see figure 11A. So this is the data reconstruction done for district. So district-wise, we did the data reconstruction. That is, I'm talking about data set A. So we can see here the red dots are actually the officially reported cases of COVID-19 in each district, and the black bold line is the reconstructed data using the DMD algorithm. So we can see that the algorithm is able to reconstruct the data quite accurately. Similarly, for data set B, so we reconstructed state versus week data using compatible window-wise DMD algorithm, because as I said, the DMD was not applicable for data set B. And here also, we can see that the reconstruction was quite successful. As we can see from here, the red dot and the black line is quite overlapping. So data reconstruction also is something that algorithms can do, very well do. Now here we have seen the data reconstruction. So this is in the real time, the data reconstruction. So the first row shows original data, and the second row, the second figure is showing the reconstructed data using DMD algorithm. And in this second figure here, we are using the CWDMD for dataset B. Is this animation visible here? Can anyone confirm? Am I audible?
Yes, ma'am, you are audible.
Is the animation visible? The data reconstruction, is it visible?
Animation is not yet started, ma'am. Picture is visible. The video is not yet started.
Oh, okay. All right. Is it working now?
Yes, ma'am.
Okay. All right. So
Now
we
it's working. Now it's visible.
okay. Okay. All right. So now actually we can see that the data reconstruction is quite successful. Data reconstruction can be in the real time. We can see that the original data and the reconstructed data, they are almost same. So these algorithms are quite effective in reconstructing the data also. Then we have performed the error analysis for the dataset B, dataset A and B. So what do we the calculated error for using the DMD algorithm for an incompatible dataset, that is dataset B, it's quite high. However, when we apply the CWDMD on the dataset, then this error goes really low. So this shows that application of CWDMD is quite accurate, the error is less, and even the reconstruction is quite good in those datasets which we cannot analyze using the DMD algorithm. So I would like to conclude with this that the prior research in India, they haven't utilized these algorithms for understanding infectious disease like COVID-19. However, infectious disease can be very nicely understood using these database algorithm in addition to the traditional modeling approach. Because if we use both traditional modeling approach and the database approach, then we can capture a wide spectrum of knowledge for these infectious disease. Because at times we need to analyze the different factors that impact the disease. So there we can use a traditional modeling approach. But there are times when we actually want to see the spatiotemporal spread of the disease. So at those moment of time, a traditional modeling approach is of less use as compared to the data-based algorithm like DMD or CWDMD. So yeah. So thank you for patient listening. And if you have any question, I will be happy to answer.
Audience, you have any queries? Ma'am, question was posted in the chat box also.
Okay, let me see if I can.
Yeah, one question is, what is the force of infection for the proposed model? One participant is asked.
Okay. I'm not able to see the chat box. Can you repeat the question? Yes. What is the
force of infection for the proposed model?
force of infection? Force of infection. I didn't understand. What is force of
Force of infection.
So I would like the person who has asked the question to elaborate the question. The question is not clear.
One second, ma'am. We give a permission
There's
to
no such thing
participants. One second.
Yes.
Participants, now you can unmute yourself and you can ask your question.
Good morning, ma'am. I'm Palak Goyal. So,
I can.
can you hear me?
Yes, I can hear you. Yeah.
It
Please
was
go
a
ahead.
wonderful talk and quite informative. Thank you so much. So, basically, my question is what is the force of infection with respect to the compartmental model you took? I mean, who are the people who are involved in spreading the infection? So, what is the definition for that model? This is what I wanted to ask. Like, you multiply beta I in simple SIR model.
Yes.
So, like that, what are the infectious compartment in your proposed model? This is what my question is.
Okay. So you can see that our model has 6 compartments. Let me go back to the slide where, so you can see there are 6 compartments, right? So we had S, E, Q, I, J, and R. All right. So you can see those who are spreading infection. Which compartments are spreading infection you're talking about?
Yes,
So
ma'am.
yeah, so that would be Q, I, and J. Okay, because so once the queue is quarantined, then it won't be spreading infection, and I is isolated once it has gone to isolated class. So again, from there also the infection would not be spreading. And once this Q and I has gone to J, which is a hospitalized or completely isolated compartment, then also it would be reducing the spread of the infection. But before that, exposed class E, it is open, and this would be the individuals from this compartment would be free to spread, or rather they would be the more possible candidate to spread the infection. Okay, because
Okay.
Q, I, J, they are all kind of isolated in one or the other manner.
Ma'am, I have 2, 3 questions more if I can ask.
Yeah, I'm fine. I have no issues.
So, ma'am, like you said, you did sensitivity analysis for various model parameters. So, can you please tell me further, like which method did you use for the
Yes,
sensitivity?
yes, sure. So actually, all the details you would find the details of the technique and everything you will find in the paper. But I would just tell you in brief, we have used for parameter estimation the regression technique, and for the sensitivity analysis, we have used the PRCC technique. You can
Okay.
find detail in the paper.
Okay. And ma'am, like it will be really helpful, like the methods that you use for spatiotemporal analysis, if you can provide any further resources to read, or like will the reference that you are putting it in the slides will be enough to learn all those techniques?
Yes. Actually, all the supplementary resources are available in my paper. You can go and see it's a Kanav Singh and my paper. He's my PhD student who has done this whole work. And the paper is in computational mathematical biophysics. So the entire detail of the supporting paper is there in the paper itself. You can find it from there.
And ma'am, like, can you provide your email address to connect with you so I can ask further things if needed?
Sure. I'm writing it now in the chat box. You feel free to contact me.
Thank you so much. It was a wonderful talk, ma'am. Thank you so much.
Participants, do you have any other queries? Okay,
Someone is asking to show the reference slide again. So I'll go back to the reference slide. I think it's visible now.
Yes, ma'am, it's visible.
And any other question in the chat box? No other question. I see there are no other question in the chat box. So yeah.
Okay, then we can come to the conclusion. Thank you, ma'am. Thank you, Dr. Neetukumari, ma'am, for your insightful and engaging presentation. We appreciate your expertise and the valuable knowledge you have shared with us today. And we are grateful for the opportunity to learn from you, ma'am. Thank you, and thank you for accepting and deliver the talk in our FDP, ma'am. Thank you very much.
Thank you very much. Thanks a lot.
And we give a round of applause to our speaker for the wonderful presentation. And we look forward on seeing you in our participants. We look forward on seeing you in our afternoon section also. So afternoon section by Dr. C. Ram Reddy from NIT Warangal. He is giving at 1:30. Please join the section. And afternoon 3 p.m. we have validity section also. Please join for the sections. Thank you. Thank you, ma'am.
Thank you. So I would sign off now.
Yeah, yes, ma'am. Thank you.
Thank you.